Okay, Unit 6, Lesson 2, Sinusoidal Function Properties. So these are some lists of online calculators you can use. Keep in mind that Desmos is also an option. Here are some conversions that you need to remember. We said that pi is equal to 360 degrees because that's a full circle. And meanwhile, pi over 2 equals 180 is another representative. Okay, so we can use this conversion because often with all of these online calculators, graphing calculators, the units are in terms of radian, which is like the pi mode when you're using the numbers itself. However, in grade 11, when we introduce you to sinusoidal functions, we use degree mode because it's a little easier to look at angles as degrees because that's what we're used to, right? As we've seen in the trigonometric function unit. So keep that in mind as we move forward. So question 1, use technology to graph the following and decide if they're periodic or not. So for the first question, for all of these questions, I used Desmos and left the print screen here. And what you're going to do is probably draw one of these like that on your version. You know, it doesn't have to be crazy good, but as long as you're doing a sketch, that makes sense. Okay, and then you're going to interpret it. So is this periodic or not periodic? So there's a couple features of when it is periodic or not. So one is that we must have the periods to be the same. And another thing you need to ask yourself, is the amplitude the same? So for this question and for this graph, when we look at all the amplitudes, we're noticing that it goes up. Oh, sorry, that's not the amplitude. Amplitude is actually just halfway. So halfway with respect to the axis. The amplitude is changing every time, and therefore we're going to say it's not periodic. Question B, y equals 10 sine theta minus 15. So when we graph that, this is what it looks like. Well, as a quick check, somewhere along here, that's going to be the axis. This is approximately the amplitude, and I noticed that the amplitude is consistent every time. And in terms of the period, you can look at it different ways, but this looks like this graph always repeats from here to here or here to here. Depending on how you look at it, the period should be the same, but the period is same throughout. And to avoid confusion, I'm going to erase one version so that you can just look at one part. So meaning my period will always be the same throughout this cycle. So as a conclusion, we're going to say that this is periodic, therefore periodic. Question C, y equals tan theta. This took me a little while to prepare because it's like introducing you to this function for the very first time. So at first you might think that it is going to look the same, but it's not, right? Tan theta also represented slope. So this is the visual of what is going on. However, it makes kind of little sense without having kind of background knowledge of what's going on. So remember that tan theta is equal to y over x, and we'll keep that at the back of our mind as we go through it. I'm going to draw the x and y axis. In order for me to draw the unit circle, and I'm also going to draw the table of values in terms of theta and y. And remember that the y in this case is equal to tan theta. And we said that tan theta is equal to slope based on tan theta equals y over x. So I know that there's a lot going on here. Let's break it down. So I'm saying to you, if I have a coordinate here, that means I have a horizontal line, right? And if you have a horizontal line, that means I'm dealing with degree of 0 degrees, okay? Remember how this is the standard position and I've moved 0 degrees. And for my 0 degrees, I am not For my 0 degrees, remember that y equals tan theta, that part is different from this y. So we do need to distinguish it because this graph and this graph is different, because in this case, the input is theta. In this case, the input is x. Therefore, you're going to get different y values. So they are different. So this and this, the y values are different. So anyways, back to this, 0 degrees. What is the slope for a horizontal line? That might be the easiest way to think of it. And the y value is therefore 0. Simply, a horizontal line has a slope of 0. Moving on to the next part. So if you have 45 degrees, okay? If you have 45 degrees, that means you have a line that has a slope of 1, it has a y and x value of 1. And remember, you can plug it in and get these values as well. So when I plug in 45 degrees into this part, I will get my y. But I just want to think about it logically. The slope of this green line is going to be 1. And I am getting it by doing like 1 over 1 is equal to 1. According to this. So moving on to the next part, the 90 degrees. So 90 degrees, let me draw this line. And in this case, this is a vertical line. What is the slope of a vertical line? Well, a slope of a vertical line is, well, undefined. If you put this in the calculator, meaning if I put that, well, this is the coordinate 0, 1, and that's the x, that's the y, so it's 1 divided by 0. And if you put that in the calculator, it'll say math error. Well, I want to interpret what math error means. It means it's undefined. I cannot divide by 0. And therefore, I'm going to put undefined here. And what does that mean? Well, we'll look at it a little later when we look at the graph. So 135 degrees. Well, I get that 135 degrees over here. And for 135 degrees, again, it's easier kind of looking at it as a slope. Well, it's a negative, it'll have a value of -1. Okay, because the slope for that line is -1. So 180 degrees, that's again another horizontal line. So 180 degrees. At 180 degrees, well, if it's a horizontal line, then the slope of that line is going to be 0. Okay, now let's try to put these two together and identify where goes where. So this is 0. At 0 degrees, it has a y value of 0. Simple enough. At 45 degrees, it has a y value of 1, which is approximately here, which I'm going to do in green. With the 90 degrees, this is undefined. Remember what these are called? We've seen this. This is when theta is 90 degrees and it is undefined. And what does it mean when you have undefined in a graph? It's a vertical asymptote. At 145 degrees, that has a -1. So that's that coordinate right there. With 180 degrees, that's that coordinate right there. It might be a little confusing, but basically I have dealt with the second half of the cycle, the first cycle, and that's that. And this part is the start of the other cycle. And one thing you should notice that is like a side note is that a period for the tan function is actually, which is equal to 180 degrees. Because if you notice, this is like halfway. And if I went backwards, that's another 90 degrees. The lines are going to confuse you, so I'm going to erase that. Quick little typo error is that I'm supposed to have 135 degrees instead. I verbally said 135, but I wrote 145. So question D, y equals 4 sine squared 2 theta minus cos theta. This is the graph I got. Get the following. And if you look at the more extended version, you'll find that it is periodic. Okay, so this is the graph that I was talking about. If you look at it from the back and look at it more carefully, this one is actually periodic. Part of the reason is you're dealing with a sum of two periodic functions, meaning if this is periodic and this is periodic and we're simply adding or subtracting, we're combining them, this overall is going to be a periodic function. Part E, this is a graph. It looks pretty straightforward, and so I'm just going to say that therefore it is periodic. Question 2, sinusoidal graphs resemble a regular symmetrical looking wave. Only 2 of the above functions are considered sinusoidal. Can you guess which ones? So B and E are the only ones that are symmetrical. Think about if you are making those butterflies as part of the art project. That's what makes a symmetric. When you paint one side and you make the butterfly and then you fold it in half and you're going to get the exact same thing. Well, that's kind of what it means to be symmetrical. If you reflect it along the y-axis, it has to be the exact same. If you fold it vertically, it has to be the exact same. So the other options are not periodic and sinusoidal, and because for part A, well, that's simply not symmetrical. It is like oscillating, it's becoming bigger and bigger. Part D, that's not symmetrical. It's going up and down and up and down. And C, it's tan theta. It's not symmetrical because if I was to reflect it on the y-axis, it will not budge and I'll get a different graph. Only B and E are symmetrical. Question 3 and 4, this is basically a review of what I already talked about in Unit 6, Lesson 1 review. We'll go through it quickly. Please refer to the Unit 6, Lesson 1, Part 1 video if you want to look at it more detailed. Number 3, it is time to develop the parent graphs of the functions that give a sinusoidal wave. Place and label the x and y axis in the following graphs in the proper places so that it would represent the sine function and cosine function. Basically, notice that it's like the exact same wave, but it really depends on where you put the axis that determines whether it's a sine and cosine. Meaning you could always write any of these kind of functions in terms of sine or cosine. So for this, what I try to remember is that the sine graph starts at 0, 0, the origin. And I have to remember, I'm not going to put it here because that way it's going to have a reflection if I do that. See how there's a reflection? I have to start it so that it starts here. That's the y-axis. This is the x-axis. So that this part is 0, 0. And my graph represents one cycle of sine graph. And notice I picked the one where it goes up and then finishes here. Cosine graph. Same idea. I need to make sure that it starts at the maximum, which is 0, 1. And then it's going to make its way down and then up. So have to remember that. It basically has like a minimum. It almost looks like the parabola facing up. So this is where my coordinate is. That means I have to draw my x and y axis accordingly. And I'll draw the x axis. That's always going to be the same. My y-axis is over there. And see how this represents one period? Where this is 0, 1, and that's one period. The way I remember the cosine graph is that it starts at the max, it goes down, and then comes back to its original spot. Question 4, for each function, outline one complete circle and highlight the 5 key points on the cycle. State reminders of how to begin sketching each type of graph. So notice it's what we've seen before, drawing my theta and y-axis first. Let's start off with the sine graph. You have the sine graph. And it starts at the axis and goes up. So I know that it has a value of 1 and -1, and those are my max and min. And the period of a full circle is 360, and so that's 360, and I know that's the last coordinate, and this is the first coordinate. And I work my way, and in the middle, the way the sine graph looks, it hits it right at the y value of 0. I'm gonna draw these little sticks to help me that this is where 90 degrees is, this has to be 270 degrees, and it basically hits 90 degrees, comma 1, and then 270, comma -1. And sinusoidal, the sine graph has this shape. So y equals sine theta has like the little mini waves, and I remember it as, okay, it goes up, and then it comes back to its original position. The cosine graph. So the cosine graph is this. And it starts at max, then goes down. So similar to the sine graph, I know it has a max of 1 and a min of -1. It ends its period at 360 degrees. This is the halfway point. So unlike the sine graph, it starts at max, which is right here, and then it's going to return to its original max position. The way it looks is that the cosine graph is one big wave. It's going to hit the minimum value at 180 degrees. And in between, well, in order to make this curve is what I'm talking about, I need to put it so that it hits the y-axis at the respective value and at the respective value. And so this is my cosine graph. This is my cosine graph.